Welcome to today's problem walkthrough. We're tackling LeetCode problem number 1012, numbers with repeated digits. This problem challenges us to count numbers less than or equal to a given value, n, that contain at least one repeated digit. It's an interesting problem that requires a mix of combinatorics and programming logic. Let's dive in. The problem asks us to determine how many numbers less than or equal to a given positive integer n have at least one repeated digit. For example, if n is 20, we need to analyze all numbers from 1 up to 20 and identify which of them have repeating digits. The input to the problem is a single integer n, which can range from 1 to as large as 10 to the power of 9. The output will be an integer representing the count of numbers with repeated digits within this range. For instance, if n is 20, the numbers we're considering are 1, 2, 3, all the way up to 20. Among these, the only number with repeated digits is 11, since it consists of two ones. All other numbers have unique digits. Therefore, the output in this case is 1. Now, if we take another example where n equals 100, we have numbers from 1 to 100, and here, 10 numbers have repeated digits. These include numbers like 11, 22, 33, and so on, all the way up to 100. Thus, the output is 10. When n is 1000, our range expands to include all numbers from 1 to 1000. In this case, there are 262 numbers that have repeated digits. These include examples like 11, 22, 333, or even numbers like 1000 where the repeated digit is the 0. This emphasizes that as n grows larger, the number of numbers with repeated digits increases significantly, making it crucial to find efficient ways to compute this without checking every number individually. The constraints of the problem specify that n can range from 1 to as large as 10 to the power of 9, which means brute force solutions that iterate through all numbers up to n will be computationally expensive and infeasible for large inputs. This highlights the importance of using optimized techniques, such as combinatorics or efficient counting methods, to solve the problem. Special edge cases to consider include very small values of n, like 1 or 10, where repeated digits are rare, as well as large values of n close to 10 to the power of 9, where the sheer size of the range can make computation challenging. Additionally, scenarios like numbers with repeated digits starting from the highest place value, such as 1000 or 9999, require careful handling in the solution. To tackle the problem of finding numbers with repeated digits for any given n, we start by framing the problem in a more efficient way. Instead of directly counting numbers with repeated digits, which can be cumbersome, we calculate the complement, the count of numbers without repeated digits, and subtract this from the total numbers less than or equal to n. This shift in perspective simplifies the task significantly, especially for very large values of n, like 10 to the power of 9. One naive approach to this problem is brute force. Here, we would iterate through all numbers from 1 to n, checking each for repeated digits. To do this, we could convert each number into a string and check if its length matches the size of its unique digits. However, this approach has a very high computational complexity of n*d, where d is the average number of digits in n. For a large n, this becomes computationally prohibitive, as it would require billions of iterations. On the other hand, a more optimized method involves mathematical counting using permutations. By leveraging combinatorics, we can directly calculate the count of numbers without repeated digits, which avoids the inefficiency of brute force. The key observation here is that numbers without repeats can be constructed by selecting digits uniquely from the range 0 to 9, allowing us to use permutations to simplify the problem further. Now, let's break down the core idea behind using permutations to count numbers without repeated digits. For a k-digit number, the first digit has 9 valid options, as it must be non-zero. The second digit then has 9 remaining options, since it cannot repeat the first digit, and the third digit has 8 options, and so on. This forms a clear pattern that can be calculated using the formula for permutations p, m, k, equals m/mk, where m is the total number of available digits, and k is the length of the number. To implement this approach, we start by converting n into a digit array to simplify the breakdown of its structure. Then, we calculate the count of numbers with fewer digits than n using permutations. For numbers that have the same number of digits as n, we use a backtracking approach to ensure no digit repeats while constructing numbers digit by digit. This method has a much better time complexity of O log n asterisk log n, as we avoid iterating through all numbers up to n. However, it is slightly more complex to implement compared to brute force. Another alternative approach is to use digit dynamic programming, or digit DP. This method utilizes state variables to track details such as the current digit position, whether the number is still constrained by n, and the set of digits already used. While elegant, digit DP introduces additional complexity in implementation and debugging, making it less practical compared to the combinatorial approach. Given the options, the strategy we chose is the mathematical counting approach using permutations, as it strikes the right balance between efficiency and simplicity. This method avoids the inefficiencies of brute force and is simpler to implement than digit DP. The first step of this strategy is to count numbers with fewer digits than n. For each k-digit number, we calculate the permutations of the first digit, which must be non-zero, and the remaining digits, which can include 0. We then sum up these counts for all lengths less than the number of digits in n. Next, for numbers that have the same number of digits as n, we use backtracking to enforce the condition that no digit repeats. This ensures that only valid numbers are included in the count. The recursion stops immediately if a digit is repeated or if the constructed number exceeds n. Finally, to solve the original problem, we calculate the complement. By subtracting the count of numbers without repeated digits from the total numbers up to n, we obtain the count of numbers with at least one repeated digit. This step ties the entire approach together and provides the desired result efficiently. When comparing the approaches, each has its own trade-offs. The brute force method is conceptually simple but far too slow for large inputs like n equals 10 to the power of 9 because it involves iterating through the entire range. Digit DP, while elegant and flexible, is more complex to implement and debug, and its performance can be slightly slower in practice due to the overhead of managing multiple states. The mathematical counting approach stands out by offering both efficiency and relative simplicity. It directly leverages the properties of digit permutations, making it scalable even for the largest inputs. By focusing on the complement, counting numbers without repeated digits instead of directly counting those with repeats, we avoid unnecessary computations. This balance between clarity, speed, and ease of implementation makes it the optimal choice for solving this problem effectively. The problem we're solving is to find all numbers less than or equal to a given number n that have at least one repeated digit. Instead of directly identifying these numbers, we take a complementary approach. We'll count how many numbers have no repeated digits, let's call this count x, and subtract it from the total numbers from 1 to n, which is simply n itself. This approach is more efficient because constructing numbers with unique digits is easier and avoids potential overlaps that arise when directly counting numbers with repeated digits. To do this, the first step is to understand the complementary problem. By focusing on numbers with unique digits, we can use systematic digit selection with combinatorics to count them efficiently. Next, we break the problem into manageable parts. First, we convert the given number n into a list of its digits. For example, if n equals 328, we represent it as 3, 2, 8. Then, we need to calculate two things: the count of numbers with unique digits that have fewer digits than n, and the count of numbers with the same number of digits as n but are strictly less than n. This sets the stage for leveraging permutations and a digit-by-digit approach to solve the problem step by step. Now, let's calculate the count of numbers with fewer digits than n. For numbers with k digits, where k is less than the number of digits in n, we can systematically count combinations of unique digits. Here's how. For the first digit, we have 9 choices, since it can be any number from 1 to 9. For the remaining digits, we select from 0 to 9, excluding any previously chosen digits. The total number of unique combinations is given by 9 multiplied by the permutation of the remaining digits, which is represented as p9, k1. Permutations are calculated as a divided by ab, where a is the total number of options and b is the number of selections. For instance, let's consider 2-digit numbers. The first digit has 9 choices, and the second digit also has 9 choices because it can be any digit except the first one. This gives us a total of 9 times 9, or 81 unique 2-digit numbers. Using this approach, we can count all numbers with fewer digits than n that have unique digits. Next, we turn our focus to numbers with the same number of digits as n. Here, we need to be more precise and count only those with unique digits that are strictly less than n. This requires a digit-by-digit approach. We begin by analyzing the most significant digit and progressively count valid options for each subsequent digit. If a digit matches the corresponding digit in n, we continue to the next digit. If a digit is smaller, we stop there, as all numbers that follow will already be counted. Finally, we combine the results. By adding up the counts from numbers with fewer digits and numbers with the same number of digits as n, we obtain x, the count of numbers with unique digits. The total count of numbers with repeated digits is then calculated as n minus x. Several key insights make this approach effective. First, complementary counting simplifies the process and avoids errors like double counting. Second, the digit-by-digit construction ensures we only consider valid numbers that meet the constraints. Finally, the use of combinatorics, specifically permutations, allows us to compute results efficiently without brute forcing through all possible numbers. To implement this, we use a few essential data structures. A Boolean array is useful to track digits already used during number construction, ensuring no repetitions. Additionally, a permutation function is crucial for quickly calculating the number of ways digits can be arranged. As for complexity, the time complexity is O(k squared, where k is the number of digits in n. This accounts for the digit-by-digit traversal and combinatorics calculations. The space complexity is O(k), which is required for recursion and tracking used digits. This ensures our solution is both efficient and scalable for large inputs. Here, we define a Python class called solution and implement the function numberDup_digits at most n, which calculates the count of numbers with repeated digits up to a given number n. Within this function, there's a helper method called countUniqueDigits that determines how many numbers with unique digits exist from 1 to m. To begin, the digits of m are extracted into a list, and its length is stored. The process starts by counting numbers with unique digits whose lengths are less than the number of digits in m. For each possible length, we calculate the combinations starting with any non-zero digit, followed by permutations of the remaining digits. This is achieved using the permute method, which we'll define shortly. Next, we handle numbers with the same number of digits as m. A scene set is introduced to track digits already used. For each digit position, we iterate through possible values. If a digit hasn't been used before, we calculate how many valid combinations can follow, again using the permute method. If we encounter a digit that's already in the scene set, the loop breaks since further numbers would no longer have unique digits. If all digits are processed without duplicates, we increment the total count to include m itself as a valid number. Finally, the total number of unique digit numbers is subtracted from n to get the count of numbers with repeated digits. The permute function is defined here to calculate the number of permutations of n items chosen from m. It initializes a result variable to 1 and iteratively multiplies it by decreasing values of m for n steps. This ensures that we calculate the product of the first n terms of the sequence starting from m. This method is key to efficiently determining the number of unique arrangements of digits at various stages in the countUniqueDigits function. By breaking the problem into smaller, reusable computations like this, we ensure that our implementation is both modular and easy to follow. Here, we start by defining the main function numberDup_digits at most n, which calculates the count of numbers with repeated digits by subtracting the count of numbers with unique digits from the total range, n. To handle this, we rely on the helper method countUniqueDigits. In countUniqueDigits, the first step is to extract the digits of the number m using the getDigits function, and calculate the total number of digits. Then, we begin by counting numbers with unique digits where the number of digits is less than the length of m. We achieve this by iterating through lengths from 1 to length 1, calculating possible numbers using the permutation function permute. This permutation accounts for the fact that the first digit has 9 choices, and subsequent digits have fewer available options to ensure uniqueness. Next, we address the case where the number of digits matches the length of the given number m. To do this, we use a set called scene to track digits that have already been used. For each digit position, we iterate over possible digits, ensuring that the digit is not already in the scene set. If it isn't, we calculate the permutations for the remaining positions using the permute function. If we encounter a digit that's already been used, we exit the loop for this position. After processing all positions, if all digits in the number are unique, we increment the total by 1 to include the number itself. The permute function is defined to calculate the number of permutations for n digits chosen from m options, which is achieved by multiplying decreasing values of m over n iterations. Finally, the getDigits helper method is used to break down the number n into a list of its individual digits. By iteratively taking the remainder when dividing by 10, we extract the least significant digit and prepend it to the list. This process continues until n is reduced to 0, leaving us with a list of digits in the correct order. This list is essential for the logic in count unique digits, as it allows us to directly access each digit and calculate possible combinations based on their values. With this, the complete implementation ensures all edge cases are handled efficiently. To solve this problem for n equals 20, we first need to determine how many numbers have unique digits. The digits of 20 are 2, 0, which means it has a length of 2. For numbers with a length of 1 digit, there are 9 valid options, ranging from 1 to 9. This is calculated as 9 times permute, 9, 0, which equals 9. Now, we move on to numbers with the same length as n, which is 2 digits. Starting with a total of 9, the first digit can be any number from 1 to 1, which is just the digit 1. Numbers starting with 1 are calculated as permute, 9, 1, which equals 9. Adding this to the total gives us 18 so far. The digit 2 is then added to the scene set to keep track of used digits. Finally, we evaluate the second digit, 0, but since 0 is already in the scene set, there are no valid numbers to add here. After adding the digit 0 to the scene set, we make the final adjustment. We check if 20 itself has unique digits, but since it does not, the digit 0 is repeated, we do not add it to the total. The total number of unique digit numbers remains 18. To find the count of numbers with repeated digits, we subtract this total from n, which is 20 minus 18 is equal to 2. Therefore, the result for this example is 2, meaning there are 2 numbers with repeated digits in the range from 1 to 20. Now, consider n equals 100. Here, we need to count numbers with repeated digits in the range from 1 to 100. The digits of 100 are 1, 0, 0, so the length is 3. For numbers with a length of 1 digit, there are 9 valid options, just like before. For numbers with a length of 2 digits, we calculate 9 times permute, 9, 1, which equals 81. Adding these, we get a total of 90 numbers with unique digits so far. Next, we focus on numbers with the same length as n, which is 3 digits. Starting with a total of 90, we evaluate the first digit, which is 1. Since the range for the first digit is from 1 to 0, there are no valid numbers to add here. The digit 1 is then added to the scene set to track used digits. Moving on to the second digit, 0, we add it to the scene set as well, but no further valid numbers can be added for the third digit. For the final adjustment, we check if 100 itself has unique digits. Since the digits of 100 repeat, we do not add it to the total. The total number of unique digit numbers remains 91. To find the count of numbers with repeated digits, we subtract this total from n, which gives 100 minus 91 is equal to 9. Therefore, the result for this example is 9, meaning there are 9 numbers with repeated digits in the range from 1 to 100. Now, let's analyze the case where n equals 321. The digits of 321 are 3, 2, 1, and the length is 3. For numbers with a length of 1 digit, there are 9 options. For numbers with a length of 2 digits, we calculate 9 times permute, 9, 1, which equals 81. Adding these, we get a total of 90 numbers with unique digits so far. Next, let's handle numbers with the same length as n, which is 3 digits. Starting with a total of 90, we evaluate the first digit, which is 3. For numbers starting with 1 or 2, we calculate permute, 9, 2. Since there are 2 such starting digits, this gives 2 times 72, which equals 144. Adding this to the total, we get 234. The digit 3 is then added to the scene set. For the second digit, 2, we calculate permute, 8, 1, for numbers starting with 0 or 1. This gives 2 times 8, or 16, which is added to the total, resulting in 250. The digit 2 is then added to the scene set. Finally, for the third digit, 1, we calculate permute 7, 0, for the digit 0, which equals 1. Adding this to the total gives 251. The digit 1 is then added to the scene set. Finally, we check if 321 itself has unique digits. Since its digits are unique, we add 1 to the total, making it 252. To find the count of numbers with repeated digits, we subtract this total from n, which gives 321 minus 252 is equal to 69. Therefore, the result for this example is 69, meaning there are 69 numbers with repeated digits in the range from 1 to 321. This concludes the solution walkthrough for these examples, demonstrating how to systematically calculate the count of numbers with repeated digits for any given n. In this section, we analyze the time complexity of the solution, starting with the first step, which involves counting numbers with unique digits that have a length less than the total number of digits in n. To achieve this, we use a loop that iterates from 1 up to 1 less than the length of the digits in n. Since the number of digits in n is proportional to log n, the loop runs at most O log n times. Within each iteration, we call the permute function to compute permutations, which operates in O n time due to its linear loop. Consequently, the time complexity of this step combines the outer loop, which contributes O log n, with the inner permute calls, which vary between O1 and O log n. When multiplied together, this results in a total time complexity for this step of O log n caret 2. The next step involves counting numbers with unique digits that have the same length as n. This requires iterating through each digit of n, which means at most log n iterations, as the number of digits is proportional to log n. For each digit, 2 main operations occur. First, we check whether the digit exists in the scene set, which is a constant time operation. Second, we perform another loop from 0 to the current digit, calling the permute function in each iteration. Since the digits range from 0 to 9, this inner loop executes at most 10 times. Each permute call operates in O log n time, making the overall contribution of this inner loop O log n. Combining this with the outer loop, which also takes O log n, the total time complexity of this step is O log n caret 2. When we combine the complexities of both steps, the overall time complexity of the solution remains O log n caret 2. Now focusing on space complexity, the solution uses auxiliary space primarily for the scene set, which is used to track the digits of n during the computation. Since the maximum number of digits in n is proportional to log n, the scene set requires O log n space. Additionally, the permute function employs constant space, as it only processes loop variables and does not store additional large data structures. The digits list, which holds the individual digits of n, also requires O log n space proportional to the number of digits. When we combine these contributions, the total space complexity of the solution is O log n, making it efficient in terms of memory usage. To understand the efficiency of this approach, let's compare it to a naive or brute force method. A brute force solution would involve iterating through all numbers from 1 to n and checking each one for repeated digits. This would result in a time complexity of O n asterisk d, where d is the average number of digits in numbers up to n, approximately log n. This simplifies to O n asterisk log n, which is significantly less efficient for large values of n. The space complexity of such a brute force method would still be O log n, as it requires storage for the digits of each number. In contrast, the optimized approach we've discussed avoids iterating through all numbers and instead leverages combinatorial calculations. This reduces the time complexity to O log n caret 2, while maintaining the same space complexity of O log n. Finally, we can analyze the best, average, and worst-case scenarios for this solution. In all cases, the time complexity remains O log n caret 2. This is because the combinatorial calculations depend solely on the number of digits in n, not the specific values of those digits. Whether n consists of small or large digits, the algorithm performs the same set of operations based on its length. Additionally, the mathematical proof of this complexity highlights that the dominant operation is the computation of permutations, which is linear in the number of digits. Nested loops and digit-based iterations add another factor of O log n, resulting in an overall time complexity of O log n caret 2. This consistent performance across all cases demonstrates the robustness of the solution. When working on this problem, there are several common mistakes to watch out for. First, instead of directly counting numbers with repeated digits, which can be challenging and error-prone, focus on calculating the complement, the count of numbers without repeated digits. This approach is not only simpler but also more efficient. Next, be mindful of off-by-one errors, particularly when dealing with edge cases like n equals 0 or small values of n. Ensure that your bounds are inclusive and correctly handled to avoid inaccuracies. Additionally, it's important to distinguish between permutations and combinations. Since the order of digits matters in this problem, permutations are key. Misinterpreting this can lead to incorrect calculations. Another frequent mistake is overlooking the reduced pool of digits when calculating permutations. For example, after selecting one digit, the available choices decrease, so failing to adjust for this will result in overcounting. Lastly, avoid using a brute force approach to iterate through all numbers up to n and manually check for repeated digits. This method has a time complexity of O n, which becomes impractical for large values of n, such as those near 10 to the power of 9, and will likely time out during execution. Now, let's consider insights that are particularly relevant in interview settings. One of the most important strategies is to focus on the complement approach. Interviewers often appreciate candidates who can break down a problem into manageable subproblems, and counting numbers without repeated digits is a clean, efficient way to demonstrate this skill. Additionally, showcasing optimization is key. Highlight how you leverage mathematical insights, such as using permutations, to avoid brute force solutions. This not only shows your technical competence but also your ability to write scalable code. It's also critical to discuss edge cases during interviews. For instance, you might encounter scenarios where n is a single-digit number or a number with all identical digits, like 1111. Addressing these demonstrates your attention to detail and thoroughness. Finally, be prepared to talk about space-time trade-offs. While the complement approach is efficient in both time and space, you should explain why avoiding brute force, with its O, n, time complexity, in favor of a mathematical solution with O, log n, complexity is the better choice. This shows a deep understanding of algorithmic efficiency. This problem also connects to several related problems that you may encounter. For example, LeetCode 357, count numbers with unique digits, is directly related and involves counting numbers that have distinct digits. Another relevant problem is LeetCode 1088, confusing numbers too, which shares similar ideas around processing digits and dealing with constraints. You might also find connections to LeetCode 1938, maximum genetic difference query. While this is a tree-based problem, it shares the theme of optimizing queries efficiently. Similarly, LeetCode 99, recover binary search tree, is conceptually different but tests your ability to handle edge cases, which is a transferable skill. As for alternative approaches, you could consider using DFS with memoization. This method explores digit combinations recursively and stores intermediate results, making it easier to code, though it requires more space for the memoization table. Another option is brute force, which iterates through all numbers up to n and checks for repeated digits. While simple, this approach is highly inefficient with a time complexity of O, n, so it's better suited for small values of n. For advanced users, digit DP is a powerful technique that solves this problem efficiently and is reusable for similar problems. However, it has a steeper learning curve and might not be ideal for beginners. To summarize, there are several key takeaways to keep in mind for this problem. Using the complement approach is not only clearer but also more efficient than directly counting numbers with repeated digits. It allows you to break the problem into manageable steps. Avoid brute force methods, instead, leverage mathematical formulas like permutations for optimal performance. Always pay close attention to edge cases and off-by-one errors, as these can easily lead to incorrect results. Finally, practice related problems to deepen your understanding of digit-based logic. This will not only help you solve this problem more effectively but also prepare you for similar challenges in the future. Great job completing this problem. To recap, We used combinatorics to solve the challenge of counting numbers with repeated digits efficiently. This problem taught us how to handle digit constraints and apply logic systematically. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!